Hey, good afternoon, everyone. It's Monday, what is this? May 13th. We're already in almost to the middle of the year. And this is Innovation Insights. So my name is Dale Brosius. I'm the Chief Commercialization Officer for IACMI and the host and moderator of this session. So thank you for joining us. A couple of slides to kind of reintroduce IACMI to those of you. Organized around the themes of convene, connect, and catalyze, with a lot of value propositions for our members. And if you are not yet a member, there's an easy way to do that. Go into iacmi.org/members. You can fill out a RFI, or request for information, and we will get back to you with information on how to do that. So I want to kind of, go over a couple of things. Been a busy spring so far. We were at JEC. We had an IACMI booth there, where we got caught up with a lot of folks from around the world, including a lot of U.S. companies. The lower left, we actually had a visit from Denise Bauer, who is the U.S. ambassador to France. And we got a chance to talk to her for a little while on the U.S. Pavilion and on the IACMI booth. I moderated a session in sustainable transportation, and our own Joni Harmon was a panelist in Women in Composites session. So along with, you can see Marcy Offner and Shelley Binion from U.S. industry as well. Big live demo area, which included members Thermwood and MVP at JEC. So good U.S. presence this year at JEC. I got the opportunity to go to South by Southwest and was on a panel session called Reimagining Energy Use with Digital Technologies. It was a pretty cool event. Lots of neat discussions going on in the energy space and clean energy transformation, smart technologies, and and of course, along with all the other activities that go on at South by Southwest. But this was a Manufacturing USA sponsored event for us, and I think very successful. At the end of March, we were also at the ACMA Thermoplastic Composites Conference. There's Derek Berry, who you'll hear from a little bit later, talking about wind energy and wind turbines. But again, a successful conference there with IACMI presence, put on by our good friends at the American Composites Manufacturers Association. And then coming up later this month, next week, in fact, we will be at SAMPE. We will be at booth A26 in Long Beach. We will be featuring one of our resource pool projects. You may have, some months ago, we had an Innovation Insight discussed this project of a fire-resistant wall panels and flooring panels for buildings that have to survive a 1 hour, fire test that goes up over 1,500 degrees. And so you see a couple of pictures here of the before and after, but very successful there. There is a full report on the IACMI website if you want to go read more about that. And then coming up later this summer is our IACMI members meeting, August 13th through 15th in Indianapolis at the Indianapolis Marriott. The registration is open on our website if you're a member. This is a working draft, but main events on Tuesday, Wednesday, Thursday, including a tour of the CMSC at Purdue, and working groups on Tuesday as well. Wednesday and Thursday with the main slate. Lots of great speakers that we've got lined up there. On the first evening, on Tuesday evening, we're having a welcome mixer at Victory Field, the home of the Indianapolis Indians, which is the farm club of the Pittsburgh Pirates, AAA farm club. It's a great stadium, great view. It's a block or so away from the hotel. So if you're coming, you're invited to come to that, and you can register on the website for that. And then our big networking reception on Wednesday night at the Indianapolis Zoo. So it's a little bit different venue than we've done before, but I think it'll be quite exciting. So just a reminder that this webinar is being recorded, and every webinar that we've done since May 2021, this is, I think, our 30th episode, is stored on that website, and you can go back and retrieve and rewatch any of those videos or catch up on ones that you did miss. So with that, I'm going to turn it over to our first presenters for today. First presenters are Scott Lewit, the president of Structural Composites Industries, and Joni Richards, who is the director of technology transfer for Structural Composites Incorporated. And I'm going to hand it off to you guys. So if you want to go ahead and start sharing your screen, you can go right ahead. And what I'll say is that one thing I'll say is that if you have any questions, put them in the Q&A panel or put them in the chat, and we will get to all of them today.
Well, thank you. And I drew this short stick, so I get to go first. And I want to thank the folks of IACMI for inviting us to speak to the group today. So we got a lot of material to cover, so I'm going to jump straight in. Of course, the title is dealing with our SBIR innovation. And so let's go ahead and go to the next slide and we'll get into it. So SCI, or Structural Composites, is one of 6 subsidiaries under the Total Composite Company, which is the parent company. And it's the entry point where companies come and discuss about their new composite design requests. So you see that they have the option to look at analysis, manufacturing, and testing the SCI offers, or TCC that is. So depending on what the output and what they are wanting, we can pass the cost savings on to them by doing that in-house. The other 2 that you see there with education, we'll discuss later in the presentation with our apprenticeship program, and then Energy Be Wind. That'll be our last slide to show that latest addition to the sister companies. So a few points to bring out here on this slide is that SCI was founded or established in 1987. It was a spinoff from the research that Scott did at Florida Tech. He has over 80 employees now and 40 patents in his portfolio. You see a long list of partnerships and customers we have on the right side. The ones that we're going to highlight today is with Wabash National. They're the North America's largest producer of semi-trailers, Trinity Rail, and then the kind of crux of this presentation is dealing with our SBIR efforts with DoD. So next slide. So this is kind of where it all got started, is a Navy SBIR that was working on a 7-meter hull design. And because the success they had with weight reduction and maintenance reduction, Scott was awarded $2.7 million to do further studies. And that's when, if you go to the next slide, other work that was done that was kind of a spinoff, and what we're really going to get into show the technologies that were discovered, if you go to the next slide, with our Prisma Perform technology and our co-cure coatings and metal hybrid composites. So again, just highlighting the fact that he's got 40 patents in his portfolio, and these are the areas that we're going to go into a deep dive on. Next slide. Scott?
Yeah, okay. So one of the things we figured out a long time ago is that depending on the market you're in, a lot of times we're all trying to solve the same problem. And what we've been able to successfully do is take technology originally geared to the Navy, morph it into the marine market, as Navy boats. So that's an easy morph. But the bigger markets that we're trying to get into are transportation and construction. And this slide, it's a bit dated, but it tells, I think, the story. So if you look at the marine composites market, it's about 68% penetrated with composites. And there's not really barriers to the use of the composites. So you don't see, we accept its performance and price in the marine market. So about 68% of the materials that could be used out of the 100, 68% are composite. If we look at transportation, where Wabash lives, it's really low. It's 3.6% here. And why isn't it being used more? Well, the materials don't perform good enough, and they just cost way too much. And the other market with infrastructure and building construction, you almost see a very parallel thing. So you got a 4% penetration in the construction market, same kind of performance and big price gap. What's interesting about the slide is now let's look at the scale of the markets, and that really tells the story. So the material usage back then, 2012, was about $500 million in the marine market in composites. Well, the transportation market at 3.6% is already over 5 times that size. And the construction market at 4% is like 7 times that size. So that really helps us focus on our mission here at Structure. An unfocused company helps us focus on our mission at Structural Composites. And what we're trying to do is take those 3s and 4% and make them into 8s, because it's really impactful. We early on benchmark Wabash. Wabash makes 60,000 dry van semi-trailers per year. The chassis is a likely candidate to go composite. You know, we're deep in cold chain now, but let's just say all 60,000 trailers went composite. That 3.6 would move to 4.1. And that would be about the material usage of the composites market. So that's one application at one builder. So you can get an idea of the scale. Okay. And that's kind of what our mission is here, is to try to make the marine composites better, defense composites better, and simultaneously move these technologies with scale-up partners into other markets. So we use our scale-up partners to really drive our technology to deployment, and we stay focused on developing new technology. So the core feeders that Joni talked about is Prisma. Prisma is a pretty mature technology. We came up with that in the mid-90s, and we're kind of the guys that took the wood out of boats, and a very successful product. It's evolving today now that the industry is really transitioning more to infusion processes. We've developed whole new lines of Prisma that have really given this a whole new shot in the boating industry. We estimate we're in about 20% of the boats, recreational boats produced in the US use some form of a Prisma. And what we do is we take reinforcing fabrics and we cast them into shape with expanding foam. So here's your dry preform. They can be custom molded to shape, or they can come out of machines. This is our machine here, runs at about 16 feet a minute. Wabash has machines doing Prisma panels for the semi-trailers and everything else, running at similar speeds. So pretty fast output, 16 to 30 feet per minute, making these commodity type preforms, which are really centered around e-glass fibers and 2-pound density polyurethane foam. So pretty lightweight materials, relatively low cost in the composites world. And by framing everything with this wrapped construction, we can make things that look like sandwiches, but they're not inside. And they can perform better than sandwich constructions at a far, far lower cost. Because if you look at composites, it's cores that are the most expensive element. And if you can't tackle the core cost, you're going to have a tough time getting into these emerging markets. After the core, next comes the resin as your next cost item. So we were able to take our technology. We had done some work in the RV market early on, which really helped. Our work in the bridge market, research work helped. So when Wabash came over here and started looking for their next technology, they could see the boats, but then they could see these other highly loaded structures. And they took the leap of faith, as you all know, that have worked with Wabash now. And we've been deployed since 16. I think were our first deployments. And we're in our 11th year working with Wabash right now. It's an embedded customer model. So Wabash research team lives right here in our factory, and we're innovating together. So the preforms are really the low-cost framing element. After you've done that, the next cost item turns out it's resin. And in our Navy SBIR, we're making shock mitigating boats. These boats have to absorb the shock energy of we decouple the hull and deck, so there's a lot of motion. Gel coats just wouldn't make it. And that was the driver, was to make tougher coatings. And if you're in the marine market, you'll know that the coatings are really problematic. About half of all warranty claim for boats surround gel coat, which is not a warranted item. So the builders really hate gel coat cracking. We overbuild our boats about 20% to prevent cracking. So there's a huge opportunity. Obviously at Wabash and Trinity, the extra 20% weight and cost is completely unacceptable, would never be able to meet our cost targets. So CoCure was a really enabling technology. And when we first started, CoCure is a bit unique. So I think it may be still the first commercially available property adjustable resin coating and adhesive system. And so what this technology does is a direct blend between your polyester chemistry and your polyurethane chemistry. We've developed compatible materials that these can mix together at really different blend ratios with the same 4 chemicals, and you can get radically different outputs. So it comes together in a gun. Here's an MVP gun that's got slave pumps on it for the urethane system. You got your resin pump, catalyst pump. And we can change the urethane constituents. And as we change that, we change our properties. So at first, we were really just focused on elongation, trying to get the, polyester is great. It's low cost, but it's brittle. If we can get the brittle nature of it gone, we're counting on the fibers for strength. We could have a resin that could perform very well. And for coatings, same thing. We don't want our coatings cracking ahead of our laminate. And so our secret decoder ring is really simple here. This is the percent of urethane mixed into in this case, a coating. So it's gel coat with its catalyst and then various amounts of urethane. And you can see nothing much happens till about 10%. Then we start to shift. 15% is an economic sweet spot. That elongation matches our inexpensive resins on our boats. It gives us about double the impact resistance, double the color change resistance, double the weathering resistance, double the abrasion resistance. And that's a nice spot to be at, 15% urethane. The urethane we're adding for coatings is expensive. It's automotive grade aliphatic urethanes. It's got to be out in the sun. So if we're making a co-cure resin, we can go to aromatic resins instead of aliphatics and drop the cost a lot. But here we're in a coating system. So you normally, because that's expensive, you're going to optimize the cost. But as you increase urethane content, you can see elongation radically changes. And you'll see in the next slide, we're up over 50% now in other studies. And we're looking at blends very, very high so that we can have this wide range of properties. Okay. Of interest, we just won a STTR with University of Tennessee to take co-cure into additive manufacturing along with concrete. So we're working on a new technology called multi-material printing, where we want to blend radically different materials. We want to be able to blend plastic, thermoplastic, fiber reinforced, want to blend metal, want to blend concrete, want to blend thermoset. And we have a lot of cool ideas, so we're happy to just get that funding. And then you could get an idea of some of the property changes. Here we're looking at impact resistance, and this was a resin used for a container, not a Wabash project, another one. And you can see the regular resin, the impact zones here. And then as we increase the co-cure level, you can see the effect on impact. Okay, so what's interesting about co-cure is you could change that blend ratio spatially over the part, and you can change it ply by ply or both. So the prospect of getting it onto a printhead where I can accurately dispense and meter and take advantage of all this property change is really exciting for us. Okay. So at Wabash, this was a really important missing link. We were working on the trailers and we're moving from metals to composite, the low-cost composites fiberglass. It's great, it's tough, it's just not stiff. And there's a lot of stiffness required in the chassis and the floor of the trailer. As the forklift is running down the trailer, if it deflects too much, the forklift gets stuck. Okay, so we had to have a certain amount of rigidity. And, carbon will do it, but glass is $1.50 a pound. Carbon's 20, 25, $30 a pound. It just knocks our budget out. So the discovery we made with Wabash on metal co-cure hybrids really was a home run. So now what we're doing is we're marrying the composite to the metal. We're stealing properties like modulus out of that and really kind of coming up with a way to get traditional materials displaced, ironically, by using a bit of traditional material. And so it opens up this kind of new space of metal hybrids. There's been a little work done in the aerospace industry, glare, for example. Most metal hybrids, you're bonding the metal to the composite. This is different. We're gonna literally laminate the metal onto the composite. So what we're trying to do is now with this new toolkit, how can we start to blend metal and composites together? And what we're finding is you can do some really incredible things. It's really neat. These are two radically different materials. Also, when you look at technologies, people usually are on one side of the fence or the other. The metal guys are trying to displace the composite guys, and structural composites, right? We're trying to displace metals. And so this new space of collaborating with the metal people from a scientific point of view, materials point of view is really exciting. And it's wide open. There's a lot of opportunity. And it shows how, radically different materials and mindsets, when you come together, things can happen. And I use this with our politics, right? Republicans and Democrats are about as far apart. And if we can come together, think of the things we could do, right? And that's where metal hybrids. So we came out 16 with the first products. And these have now been field tested. The reefer units that are running these units run on diesel. They're seeing about half the hours of runtime from conventional vans. About a year ago, Wabash discontinued all the conventional cold chain, only doing composites. And they've expanded all the way down into final mile delivery. If you've got Kroger delivery vehicles by you running around like we do down in Florida, those are all coming out of the plant up in Little Falls. Notably, they bought the Larson Boat Factory up in Little Falls. So they got a 53-acre, 550,000 square foot complex up there with a really good trained workforce. Okay. Our model is collaboration. We have a collaboration model, and at the highest levels, we offer exclusivity to certain customers. So Wabash is an exclusive equity customer of TCC. So is Trinity Rail. And when you come in, you get all of the IP. So we're able now to take the IP from Wabash, bring Trinity in, and pretty rapidly adapt our floor technology to a rail car. And so now you can kind of see that framed construction under there, the Prisma framing inside. And this is a 72-foot rail car home run, just a home run. We took 4,500 pounds out. We increased cube space. We actually are lower cost than steel. So it's just a total home run. That won the CAMX award in 2021. Okay. And I think everybody at IACMI knows the collaboration with the team at IACMI and University of Tennessee on our composite bridge deck. This is kind of how the sausage is made. So you can kind of see it's really simple to make, single skin panel, Prisma beams on it. You basically make two of these, you put some adhesive on the cap, you flip one onto the other, and then you cast a CoCure deck. That deck is CoCure formulated as a wear surface for roads with rocks in it. And that actually passed the DOT wear test. So that bridge is now coming on year 3. And we're hoping to get a couple more done in Tennessee soon. So it's pretty exciting. Of interest on this is we're going after highway bridge decks. And we did this deck as a demonstrator. So we have an on-ramp, an off-ramp, and a joint, thinking, okay, that'll demonstrate highway decks. What we discovered is there's a tremendous need for these little rural bridges. And the deck went on in like literally about an hour and a half. The rest of it was made conventionally and took too long, all the conventional concrete. So we're working with the team at IACMI at UTK to see if we can, especially with that additive manufacturing, is there a way we could do all this stuff so we can come on site and maybe do a bridge in a day or two, the entire bridge. But the deck shows you the potential for that. And that there's tons of small communities that are in desperate need for this kind of technology. Okay. And then a little bit on our training. So we've been working with Florida Tech. We're a spinoff of Florida Tech. And one of our interns has a real passion for workforce training, Dominique Gentili. I think some of you might have met her. And she took our intern program and really amped it up and turned it into a formal program. Last year we're 85 people. We had 16 interns last summer, 14 the year before, and they did wonderful things and really helped the company. We got patents and led to us winning a pretty significant grant I'll talk about here. And it's really important because these workers are really going into the market. So I think 4 of the Wabash hires are coming out of our intern program. Our customers are starting to hire these guys. They already know everything. And, we intern a lot more students than we can hire. So for everyone on the audience, if you're looking for quality interns, hires that know composites, we've got quite a source here down to structural composites. So the state caught on to our program and encouraged us to write a pre-apprenticeship program. They wanted to see us drive the technology out of college more into workforce. So Dominique and 4 of the interns in that first year wrote the proposal, and we won a $1.1 million grant to develop the advanced manufacturing pre-apprenticeship program. We made this for what we need. And so we give them production technician, ISO training, composites training, synthetic engineering. It's a great 6 months immersion that lets students figure out where do they want to go. Okay, we just graduated 18 out of the first class, and this is leading to more stuff. We're tied to the Space Coast Consortium apprenticeship program. And together, the Space Coast Consortium Apprenticeship Program with IACMI and UTK and NREL has just submitted a grant a couple of weeks ago we're trying to get $8 million to take our pre-apprenticeship programs and apprenticeship programs in Florida with the team in Tennessee's help, juice them up, make them the best they can be, develop a replication model to replicate those across the nation, replicated in Tennessee. So that would be that first effort. We have a proposal in, and we're supposed to hear hopefully by July or August on that one, which would be really nice. Worth mentioning, UTK has developed an incredible educational ecosystem reaching all the way down into kindergarten. It's amazing what Uday's done there. This would complement it very nice. So they don't have any pre-apprenticeships or apprenticeship programs. This cross collaboration could be really exciting at helping attract people into our industry, which I think everybody agrees is vital. Okay. And then lastly, just for those of you who are at CAMX, our partnership now with BE Wind. And this is neat. Vertical wind turbine. This is small wind. And small winds doesn't get a lot of attention. These are really neat turbines. It fits a nice little niche market because almost all the applications, they're branding combining with wind energy. And if you were at CAMX, you saw the CAMX display. This has got fiber optic lighting in it. That's a product called Lamlight. That was the intern project 2 years ago that they worked on, and we got patents on putting fiber optics into our composites to let it light up. So you can have your logo lit up, and you can put these on your buildings and fly the green flag on it. And for me, I've got my long-awaited entry into the wind energy market to demonstrate our technology. So hopefully we can do more. Also of note is in a DOE SBIR, we developed we took our CoCure metal hybrid technology and made kind of an obvious conclusion. Why can't I make tools out of that? And so this was actually a part for the blade. He had a metal blade as an option for that front shield, the metal shield for that as an option. And we took that shield and laminated it with CoCure and turned it into a mold. That mold will last probably 200 years, the rate. But this was intended for higher rate automotive production, looking at volumes at about 20,000 a year. Low rate automotive, high rate for us. Okay. All right. So that covers the company and what we're doing. I know it's a lot quick. We're hopefully you got some questions, but we're happy to take any questions. And I will say that we have a passion for what we do here. We love what we do. It's taken 30 years to figure out where we want to go, and we know what we are now. So we like developing technology. We'd like to have our collaboration partners. We're really collaborators at heart, and we collaborate with big companies, small companies, and hopefully we can collaborate with you also.
Thanks, Scott. Thanks, Joni. I'll give time for people to put some questions up, but one I've got is, this thing all started with an SBIR project with the military to develop the CoCure. And where did that eventually go on the DoD side?
Yeah.
It came back, you had to come back around to it, I think, right?
Yeah, sure. So just a point, Dale, the company actually started in '87 with a SBIR from the Navy on fire performance. Okay, so that's way back. All right. But in 2009, we won the one for the lightweight combatant craft, which led to CoCure. And so now, 2012, I had figured out CoCure, mixing, homebrew. And I went to the chemical companies with this invention. And I went to the big guys like BASF and I said, here, look at this cool technology. I can make the properties change. And they said, oh, that's nice. They sell me, I buy foam from them for our stringers. So they had to listen to me. So I couldn't get much interest because they said, well, how many boats does the Navy make? Well, they make like 150 boats a year. So they're all about volume and money. And I sort of get it. I'm about technology. So fast forward, really only a few months later, Wabash found us and we're collaborating. And as they're evaluating whether to join us here as partners, they saw the CoCure technology, it was patent pending, and they reviewed it and said, this is really cool stuff, and jumped on. Well, gee, the supply chain just pivoted 180. So as soon as I had Wabash, the world's largest trailer producer, on my side, now I got tens of millions of dollars of supply chain investment to make CoCure commercial, not for the Navy, for the semi-trailers. And so that deployed. And then, as Joni said, I kept applying for something called Rapid Innovation Fund, which is another deployment tool that the government has. And now that CoCure was a commercial product, I was able to get a $2.6 million Rapid Innovation Fund project. So this is that process I call technology stair-stepping. And the lesson to the government guys is a lot of inventions, need that commercial pull to get the supply chain to engage, to make them a reality so that the government can benefit from it. Okay. And I consider that so we've got, good boat technology. The CoCure's moved into an Army platform. We're in a radar system there. We've been on some prototype systems for amphibious aircraft. And, we're actively trying to move into other markets with it. Metal hybrids being really getting a lot of interest right now. So I expect in the next year, you'll see some platforms with metal hybrids. That's all I can say. More.
Scott, I was just gonna, somebody had asked if they could have your email address. Is it okay if Kim puts your email address in the chat?
Yeah.
Okay.
Yeah.
All right.
Well,
And then, while you're at it, your social and your mother's maiden name. Yeah. So, another question. I mean, looking at that lower picture, lower left picture, that's how much of that is a single infusion, or what's the largest single infusion in that trailer?
The trailer, so they're kind of a hybrid wet compression molding process right now.
Mm-hmm.
All right. And so the components are all 53 feet long. So you got a single piece floor, you got a single piece roof, single piece sides, single piece nose, and then those all bond together to form the trailer. Okay. Does that answer
it? Yeah. What's the mass of all of that?
I'm going to guess. I want to say it's around 7,000 pounds, 8,000 pounds, but I'd have to kind of guess it. Now, bigger, the floor is 72 feet long, but it is still molded in two components. We decided to break it up so we could ship it and put it in the way it's supported. It works fine. So I would say in the transportation world right now, that 53-foot is the biggest molded component. In the marine world, it gets bigger, right? Like we do the Hydrosport 68. It's a bigger platform.
Okay, good. Last question I got is, okay, so and it comes back to the workforce development. So you bring in all these pre-apprenticeships and apprentices, and in Florida, and a bunch of them are heading up to Little Falls, Minnesota. How do they, are they handling the transition pretty well?
Yeah. So actually, the ones that are here because they're on the research side, and we're doing all the research right here. So as Dominique is matching people, something that's really important, right? Because she'll find the intern for you. Okay. And then part of that is finding an intern who's going to want to live where you're talking about, because it doesn't make any sense to bring an intern in. We're looking to get these people employed. We want to get them to get jobs. And so it's part of that matchmaking. So as she, and for those in the audience that want to tap this, once they know, and if it's Little Falls, they got to know that ahead of time. And as part of the internship, we would at least have to fake it, if you know what I mean. But, right now, most of the applications and jobs are here and a good bit up in Indiana. And so, Wabash has a pretty big innovation team, and the innovation team isn't housed at Little Falls. The production is. Right.
Yeah. So the innovation team's housed in Lafayette.
And some down here. Yeah.
Yeah. Okay. Good. All right, so, you know, if anybody else
And
has
just
any
to make a
questions?
mention
Charles,
too,
you said?
something about innovation teams,
Right.
I have to say. If you don't have one, and if you're a larger company, like over a couple hundred people, you should really consider having innovation teams, especially the big companies. And one consistent thing I see throughout the ecosystem is companies that have developed innovation teams are able to better innovate. Go figure. If you don't have one of these, man, you're banging your head against the wall all the time. And so, you know, I can show you a lot of examples. And if you're in a big company and you're frustrated, talk to us and maybe we can help you talk your management into creating one of these, because it is a game changer.
Thanks again, Scott. Thanks again, Joni. And we'll again, if you've got any questions, and you can put them in there, or obviously you've got Scott's email address in the chat, and you can send to that as well. Okay, so we're going to move to the next presenter today, and we've only got two sets of presentations today. So, you know, we're going to give Derek Berry, who's a senior wind technology engineer at the National Renewable Energy Laboratory, chance to talk about the research that's been done there under IACMI and the capabilities that are available to the community writ large at the COMET facility in beautiful Colorado. So, you know, totally different landscape than where SCI is located. So, Derek, over to you.
Yep. Okay, great. Two questions. Can you hear me, Dale?
I can hear you, and we can see your presentation. So.
All right, great.
I don't know what your second question was.
Yeah, awesome. Great. Thanks. Well, thank you so much for having me here and giving me the opportunity to talk a little bit about the great research, IACMI, a few other types of research as well going on at the COMET facility. I'll go ahead and get started here and advance my slide. So I'll introduce you to the COMET facility, the Composites Manufacturing, Education, and Technology facility. It's right there in the middle of your screen, the small Quonset hut. I'll go to the next slide that kind of flies in and shows you here. At our Flatirons campus near Boulder, Colorado, NREL is located at Golden, Colorado, our main campus, and then this facility up at our 20 miles north near Boulder. And we do a lot of research at the COMET and then hold different events like the one you see on the screen here was one of our Composites 1 IACMI workforce development and demonstration events at the COMET. And we just had one this past February as well. So the COMET was founded around 2016, the fall of 2016, as we were standing up the initial phase of IACMI. And so really a collaboration between IACMI, NREL, the state of Colorado, and many of our other core partners and companies that are organizations and companies that are part of IACMI. About 10,000 square feet of advanced composite materials and manufacturing research that goes on there. Two things that are really important about the COMET. One is research at scale. And we're not talking about the scale of very large wind turbine blades that are commercialized today. I'll get into that a little bit later. But scale going from the gram level and the kilogram level panels and substructures up to full scale blades. And for us, full scale blades is 13 meter, maybe 9 meter blades, things like that, and going a little bit larger here in the future. But a very good platform, to optimize and innovate on wind turbine blade research. And to iterate fairly quickly and then develop solutions that we can help commercialize with the wind industry. And then the other is just the private-public partnership. Everything that we do through IACMI, through NREL and DOE is with the wind industry, the U.S. wind industry, the global wind industry, the supply chain associated with that. And so those two things are really, really important to the COMET facility. You can see on the screen there some of the capabilities and the research projects that we've engaged in between our founding in 2016 through today. I have through 2022 there. We've expanded a little bit more. We're constrained by space, especially overhead space a little bit, and we're looking to actually move into a new facility, develop a new facility on NREL, but that takes some time with DOE. So it is the inside of the COMET is in many ways functionality like a wind blade manufacturing facility, not nearly as big, but it can function kind of doubles as other capabilities. You see there in the top picture that we have a tour going on at the same time we're doing some research with our core partners. And so we have tours, we have visits from our partners working on research projects with us. We have different types of research from small scale to large scale going on there all the time. We focus on wind turbine blades mostly, and there are some other structures I'll get into as well. But a lot of that is in the form of infusion composites. This just gives you an idea, this video, hopefully that's running on your screen as well, of some of the research we do. This is a 13-meter blade mold there, and we're performing the layup and the infusion here of two skins, a high pressure and low pressure skin, and then also the shear web, and then when we assemble the blade here, and then that can go on to our test stand. We have a full validation capabilities, which I'll get to at the end of our this presentation as well. But that's generally what you'll see in the Comet, but it can be this type of scale, it can be smaller scale as well. So just to kind of give you an introduction to the Comet itself and what this looks like, I'm going to move on to the next slide here. What I want to do is talk about how this applies to the wind industry and the growth of wind turbine blades. So when I got into the wind industry in '95, we were producing thousands and thousands of 9-meter blades at TPI Composites, where I worked for about 15 years. You can see Steve Nolette there in one of the pictures as we're producing these 9-meter blades. And pretty primitive approach to it all. And even back then, we were looking at scaling up at that point. This is a picture I took in the Netherlands, actually, in about late 90s. And you can see we're already repowering blades, and many of our blades were being taken down. And at that point, just put into piles. And that'll get to some of the sustainability research that we're doing that I'll talk about a little bit later in the slides as well. Already back then, nobody in the late 90s was really thinking about recycling those blades. And you see just kind of in a pile in the field. However, that would come along a little bit later, right about when IACMI was started in 2015, 2016. We're also looking at scaling up. What do those larger blades look like? And so we started thinking about what flatback airfoils look like, larger roots compared to the max chord and things like that. And so eventually these blades have grown, and many of you have seen charts like this. That they're well over the size of a jumbo jet of a Boeing 747, can fit in not only the diameter of the swept area of the turbine, but the blade size as well. And this is just a picture of what the GE Halyard 12 megawatt Halyard X 12 megawatt turbine would look like next to some of the largest structures in the world. These are pretty big wind turbines and wind turbine blades. And so that gives us the opportunity to understand what our materials and manufacturing research has to be tailored in order to be able to go into the factory and help commercialize new technologies, new innovations through IACMI and through NREL here. And you can see the kind of what that looks like in the blade factory. This is a GE 107 meter blade that was produced in Cherbourg, France, at their facility there. And then they're one of the first blades produced there, 107 meters long. The scale here with all the people that actually manufacture this blade standing outside next to the blade gives you a sense of what we're working on for scale and what that means as we scale up and work with companies to commercialize new technology. So then let me hop back into some of the research that we have been performing at the Comet facility with our partners through IACMI projects and some other non-IACMI projects as well. One of the major early research projects that we jumped into was looking at reversible thermoplastic resin systems for recyclable blades. And in this case, we partnered with Arkema and their Ilium in situ polymerized thermoplastic resin system. And we did just what we talked about before, started at small scale, started at very basic thin panels and coupons, and then scaled that up to the 9-meter blade you see on the left-hand side here, that won an R&D 100 award. And then from there, over to our validation. You see the third picture that we have that on our test stand at the STL, the Structural Test Laboratory here at NREL, which is right across the street from the Comet. And then eventually industry kind of took this further in Europe, mostly the Zebra Consortium. You can see the members of that and the top right hand of the screen, and produced some 62 meters and now 70 plus meter blades using the Ilium system. What we want to do, however, this is kind of reached a point where the next step is to get these onto a turbine and for flight testing. So we're looking for IACMI 2.0 opportunities to actually, with a new turbine coming to NREL out here in Colorado at the end of this calendar year or beginning of next calendar year, put three flight blades using this made out of Ilium resin, thermoplastic resin system, and kind of make this the final test and get this commercialized in the wind industry. So this has been a pretty successful project that we started very early on in IACMI, probably one of our first projects back in 2015, 2016. This also led into looking at thermal welding. If we have a thermoplastic material, can we, instead of using adhesive in the bond joints in a blade, can we look at thermal welding? And so we did a lot of work in the COMET with the organizations you see in the upper right-hand side there on an IACMI project to kind of prove this out. And you can see we had some successful trials of actually, instead of using adhesive, bonding paste adhesive, we used resistance welding and thermally welded different structures, high pressure, low pressure skins together. This has a lot of work to go. We proved out some of the possibilities here, but to scale it up, to deal with the tolerances on a 100+ meter blade, to deal with the energy sources needed and things like that. A lot more work has to be done in order to commercialize this, but we did a lot of the basic research to understand that it could be done on a fairly large scale to potentially down the road eliminate the weight and the weak spots, the failures in the field of adhesive bonding. I'll move on to a little bit different. Blades have always used, when I say always, for the past 10 years or so, spark caps that are pultruded, whether carbon fiber spark caps that are pultruded or glass fiber spark caps. When I got in the wind industry 30 years ago, we were using hand layup for unidirectional or pulling toes through wet baths and things like that. But really, we revolutionized the way that wind turbine blades were made, and specifically the spark cap, by going to pultrusion. One of the things that we did with an IACMI and with Oak Ridge National Laboratory and pultruding at Strongwell in Virginia was to look at textile carbon fiber and looking at reducing the cost of the carbon fiber input with larger toes and material properties tailored to what wind turbine blades, the stiffness that wind turbine blades require. That is still an ongoing work with Oak Ridge and understanding how we can commercialize a textile carbon fiber for wind turbine blade pultrusions. But we did a lot of the basic research here in 9-meter blades and in 13-meter blades as well, installing these pultruded spark caps that we pultruded at Strongwell. I'll switch to another project and really kind of one of the later projects in IACMI 1.0. It was led by University of Massachusetts Lowell, UMass Lowell, and Steve Johnson there to develop a techno-economic model, an Excel-based techno-economic model that can help to optimize wind turbine blade manufacturing. And we did some trials in the COMET, you can see here during COVID. And we produced 3 GE 56.9 meter blade tips, about 9 meters long each, and looked at actually a method that we could, instead of having 2-step closes for wind turbine blades, develop a 1-step close where we infuse the shear web into the lower skin here, you can see there, and then just have 1 step to close that and cure the bonding paste as we close a blade. So this led to a really great working model. Steve Johnson developed the whole thing, and it can be used by industry today in order to model optimizations to blade manufacturing, materials and manufacturing, to understand paths to commercialization for new innovation there as well. And then I'll finish off with some of the work we've done in automation. So we've had several IACMI projects, and then a follow-on project outside of IACMI. And then right now, our very first project in IACMI 2.0 will be taking up where we left off on our last automation project with LM and GE Vernova, used to be GE Renewables, now GE Vernova, and looking at automated trimming, automated grinding, automated sanding. And we have made a lot of strides here. I'll go to the next slide and look at some of the trials that we've been doing recently with our robots in the COMET, and using a section of a GE blade, an LM blade here, that we have been up to the North Dakota plant, the LM North Dakota, Grand Forks, North Dakota plant, and trialed some of this. And we will, part of the IACMI 2.0 project that we start, will be deploying this fully in the Grand Forks facility in North Dakota, and then eventually, hopefully, around the world and many LM factories. And this technology and others like it, we can develop for the wind industry as a whole for different finishing processes, but maybe even molding processes as well. I'll just finish off talking about some of the ongoing and other future wind blade research. I know I'm running out of time a little bit here. We have a project outside of ACME now, looking at wind turbine blade core, led by Andy Bridge and AES, TPI Composites, Orion. IACME is part of that.
Derek, you've got plenty of time. Don't feel
okay,
rushed.
great. Thank you so much. Yeah, thanks, Dale. So we're working on that project right now, looking at 3D printing core for wind turbine blades that can be net shape of the blade itself, larger panels, and reduce defects in the field, and reduce cost, and look at supply chain issues as well. Then we also been working with others. Orbital Composites has been working on some different additive manufacturing approaches, as well as a new company, Perseus Materials. Dan Lee and John Feist have started that company, and they're also looking at unique ways to look at production of blades with additive manufacturing. We've been working with Siemens Gamesa Renewable Energy on a future project for modular blades, continuing to look at NDI, NDE, non-destructive evaluation with Vestas and LM Wind Power and GE Vernova as well, and other companies, to look at maybe automating some of the NDE that happens in a factory or also out in the field as well. And then with offshore wind coming online, there's an amazing amount of research that can be done there for lightweighting up on the top of the tower, especially as we move towards floating wind structures, and also just supply chain, looking at the reducing any of the hitches in the supply chain right now that we have for wind turbine blades coming into this country, whether that means domestic manufacturing or just mitigating any supply chain difficulties from offshore. And then finally, I want to mention workforce development. We do a whole lot of workforce development with IACME, led by Joni Harmon and her team there, and looking at not only some of the workshops that we hold, and also reach out to community colleges and universities and doing a lot of work with them, but also thinking about our new technologies, our new materials, new technologies, as companies like GE or LM or TPI or Siemens Gamesa or Vestas opens up new factories in the United States, and we're using new innovation like the automation that we looked at before. How can we develop programs to train the workforce in that new innovation, and also just train the workforce in composites in general? When I've opened many plants around the world for wind turbine blades, and the one in the United States was in Iowa, and when you hire 400, 500, 600 people and have to train them in composites, that's not an easy task to do. And so whatever we can do with IACME to help kind of develop that workforce training, that regimen, and standardization of that workforce, that'd be great. I'm going to skip over to something that's not wind, just one picture here. We do a lot of other composite materials and manufacturing innovation at NREL, at the Comet facility. This you see here is a Verdant Power. We use the Ilium thermoplastic resin system and deployed these tidal turbines in the East River in New York City for 6 months, and then took them up back to NREL and did a lot of post-operational testing to see how they fared in the ocean, the salt water there in the East River. I'm just going to mention really quickly wind turbine blade sustainability. Obviously, I mentioned it before. It really was something that was not on our list. It was not even a concern of ours for 20, 30, 40 years of wind until about 2015. And when we started with IACME, we talked to every wind turbine OEM and wind turbine blade manufacturer, and it has risen to the top of their list from the very bottom of their list, or non-existent actually. This picture, one of many from Bloomberg article, now maybe about 4 years ago, I think, kind of sparked the debate in the public about the sustainability of wind turbine blades, the circularity of the materials in blades and things like that. Most of the turbine is recyclable, very easily recyclable, the steel and other components, but the foundation and the blades and then the rare earth materials are of note as well. But blades typically end up in landfills. So we have a kind of a dual issue to deal with here. The existing thermoset blades that were never designed for recycling, that never thought given to them. And then also, what do we do in developing blades of the future to design them for recyclability? You can see here is some of the circular economy pathways for blades. We want to extend the lifetime of the blades, although it doesn't always work when we have a repowering. You're not extending the lifetime because you're putting longer blades on and taking shorter blades down. And you have to figure out what to do with the blades at that time. But we can reuse those blades, repurpose them for something else, different structures, And then a recycling, we're doing putting a lot of work into recycling blades that are coming off towers now. And then the sort of the last thing we want to do with them is put them into a landfill. I have incineration in there as well, cement co-processing incineration as well, which is sort of a downcycling type activity. So that's kind of the hierarchy of what we're looking for. And then we have developed here at NREL a bio-based resin system called Pecan. Robin Murray and Nick Rohr and others, other chemists here at NREL, are looking at new materials that are bio-based so that the greenhouse gas emissions of the carbon footprint of the materials that we use to develop and produce these resin systems bring a lower carbon footprint, but also then are recyclable by being able to be reversible thermal sets here instead of reversible thermoplastics. The chemists are putting a cleavable link, I believe. I'm not a chemist, in the system in order to be able to reverse this at the end of life. So then finally, I'll just finish off with a couple of pictures of our full-scale wind turbine blade validation. This is actually a picture of how we used to test blades. It's not great, especially for the guy standing underneath the blade there with all the sandbags stacked on top. We've gotten safer and better at what we do. Across the road from the Common, as I mentioned, at the NREL Flatirons campus is our structural testing facility, STL, Structural Test Laboratory. And you can see a setup there for the 13-meter blade going through a static test with a wiffle tree. We call that a wiffle tree, where we kind of spread the load out between different saddles, and we test that generally in 4 directions: max flap, min flap, max edge, and min edge. And then we move on to fatigue testing, and you can see there we're using a resonant an actuator moving at the resonant frequency of the blade itself in the flap-wise direction. We also then switch that actuator around on top of the saddles in order to test this in the edgewise direction as well. And this can be done at any scale, but for us, it's we can test up to about 30 to 40 meter blades in our test facility. We also partner. I helped design and build the WTTC in Boston, which can test up to about 100 meter blades there. They just actually put an extension on there, and I'll just run this video. You can see this is a static test of a blade, about a 50 meter blade here that is about to break, and that's a static test, and that's a pretty spectacular blade break. It's oftentimes they just fold in half pretty unspectacularly, but just a static, the static test of failure to understand what kind of safety margins you have on the blade itself. So that is the end of my presentation. I will stop sharing and look to answer any questions if there are some out there. Thanks for your time.
Great presentation. You covered, the whole thing, soup to nuts.
A lot of stuff.
Yeah, we had one question come in, and was, have you looked at urethane foam cores in the past for blades? Or what are the current foam cores, and and have you looked at urethane? Yeah, sure, we have. And so we typically blade cores towards the root section. On the inboard section of the blade is oftentimes balsa wood, contour cut balsa wood to go around the curves. That soaks up a lot of resin during the infusion process to become a little bit heavy, but that balsa core works pretty well, good compression strength towards the root of the blade. We have looked at urethane. We've used some in PVC foams and other types of foam towards the tip of the blade. We've used some recyclable foams as well in the past during our research, but but typically PVC foams that we've used in wind turbine blades. Dale, do you want to add anything to that? PET, right? Yeah, exactly. Yeah. PET, particularly recyclable PET. Mm-hmm. Yeah, the recyclable PET. Yeah, exactly. Yeah. So we have one question. One question, and then we'll be at the hour. It would be, if you had to name 1 or 2 or 3 top priorities for the wind industry that industry could bring forward solutions for, what would it be? Sure. I'll say this: reliability in the field is an issue, no question. We've overcome so many obstacles in the 30 years I've been in the wind industry, but we still have blade failures related to leading edge erosion, to lightning strikes out there. Lightning strikes, we've got a pretty good handle on with the lightning protection system, but new materials, new toughened materials for leading edge erosion, and manufacturing approaches
and materials that can reduce failures in the field, whether it's bond line failures, fatigue cracks, as I mentioned, the erosion, the leading edge erosion. That's one of the major things. And as we move offshore, it's much more difficult and much more costly to do the maintenance on those blades offshore. And so it's even more important to get good results from the process in the factory, so we have better reliability in the field. The other is automation. We've been trying for 30 years to introduce automation. We're making good strides here in order to keep wind turbine blade factories in the United States. Automation is going to be one of the key parts of that, reducing the cost of the labor in the United States and enabling blade factories to be here as we develop offshore wind. So those are two things I would say.
Okay, all right, yeah. So Scott had posted, that question about embedding fiber optics or structural health monitoring. I know that's something that's under consideration as well.
Absolutely, yep, absolutely.
Yeah. Okay.
Yeah.
All right. Well, we've hit an hour of our show and managed to fill it all up, and so. I want to say really appreciate presentations from Scott, Joni, and Derek, and thank you again. All of this will be available within the next couple of days online to review if you want to watch it again, or forward the link to folks that might want to watch it. Next episode is Monday, June 17th, and we will hopefully see all of you then. Thanks again, all, and have a good week.
All right, thanks everyone.